Test. Okay, so it's a couple minutes early, but I'm going to start. And let me just begin with announcements. I'll send whatever I'm going to say also in an email. So we have two things left. There's a lablet and a homework that's due this week. And then we have a final exam next week, and then we'll be done with the course. So just a couple things about the final exam. It's on Tuesday at 1 o'clock, and it's going to be in Marcus Hall. Okay, that's been on Spire and on the class web page since the very first class. I'll send a reminder about this. Final exam is 2 hours long. There's a little bit more time than the midterm. And as I said previously, we will only have lectures 13 through today's class on the final, which is all the material since the midterm. Okay. Typically, we have had it comprehensive, but then I decided this year just to simplify it a little bit. So you don't have to worry about the first 12 classes that were already covered on the midterm. Okay. Just focus on the latter half. I gave out a sample exam. I gave out some review material, so you can use that as a basis to study for the final. Okay, and then we will have the lab grading done. Lab 2, that is not 3. 3 just came in, right? Not lab 2. Excuse me, lab 3. Half done. Okay, so lab 3 we will have it done by end of this week, and have it back to you before the final exam. If you have any questions, you can always submit regrades. All right. So the and then is there anything else? We'll also get the lablet and the homework done soon, because we have all of this last minute stuff. We'll get it all back to you. Say. Okay. All right. So let's start. Today's class is the last class of the semester. Is going to be on security, and specifically how security intersects with distributed systems. Okay. So the thing that you want to keep in mind is, because you now have a system where components of that system are interacting over a network. That was the definition of a distributed system. Any component of the system can not only be accessed by users of the system, but adversaries outside the system, because the system is accessible either over the internet or a network. Okay? So what that means is, while if you have a centralized application, you could just run it on a machine. The machine doesn't even have to be connected on the internet. Distributed applications, you really need to think about securing your applications. Otherwise, you will see that there are unauthorized access or other issues that crop up. Okay? At least some of you saw this also as part of your cloud lablet or lab. When you started AWS instances, we saw that some of your instances got attacked, okay? Because they had a public IP, and then there are bots that are going and trying to attack every machine that appears on the internet. So there's something we got to think about and take seriously. So today we will do a very quick overview of the issues in distributed system security, some high-level techniques that can be used. And towards the end, I'm talk a little bit about how security concepts can be used in distributed systems rather than making them secure, used in the context of electronic currency and cryptocurrency. So that's what we'll do. So let's start with essentially a little bit of a definition about what security and privacy mean. So first thing is, these are actually different concepts. They sound similar, but they are not. They are related but different. Security essentially relates to things like unauthorized access to resources. You're trying to get access to data, computing resources to which you do not have access to. Usually you can use this unauthorized access to steal data. You could, for example, get access to a bank's computer or database and steal sensitive credit card information. Okay, that's an example of a security issue. Okay? Privacy is not the same as security. Privacy violations can occur without any security violations altogether. Privacy also relates to getting access to data that a user did not wish to share with you, but you can do this without, for example, unauthorized access. One example of a privacy violation is you have a mobile app running on your phone. It's collecting location information because you gave it access. Now, the user, not the user, the developer of this app can use that location to do more targeted advertising, or can see sensitive information like your phone is being seen in a doctor's office. So then you went to the doctor, you may be sick or something like that, right? So that's an example of a privacy violation. Unintentionally, some information got leaked without the user wanting it to be, right? There was no security problem there, but still some data got leaked, right? So that's a difference between security and privacy that you should think about. There's a lot of important privacy issues in the context of machine learning that I will not, of course, talk about, but something you should know. For example, you can take a neural network and probe it and try to understand some characteristic of the training data that was used to train it, right? Something that maybe whoever trained the neural network did not intend to happen. So that's another example of a privacy violation, similar to the mobile app example. Okay, again, no security but privacy. But as far as today's class is concerned, we're only going to talk about security, not privacy. Okay, but so let's, with that background, start with security. Okay, so I'll start with something very simple, which is authentication. Okay, authentication is a mechanism that allows a user or a system to prove to another system who they are, right? So it basically provides the identity of a user or a system to another entity in that distributed system. So let's take a very simple example. You get a phone call from your bank that says they're calling from the bank. They need to verify something and ask you for some sensitive information, like maybe your ATM card number or a PIN number. Of course, you can't just trust somebody who's calling you over the phone. So you have to verify their authenticate their identity, right? So how would you know that a remote entity is who they claim to be? That's our authentication problem. Okay, so we'll go through a set of protocols to design an authentication protocol. Okay, so first thing is, if we will use the standard terminology that you use in security, the two entities will be called Alice and Bob. Right? So these could be computers, this could be two users. One of them could be a user, another one is a computer. We don't care from our perspective. We'll just use these two entities. Alice is trying to authenticate themselves to Bob. So if Alice just sends the username saying, I'm Alice, okay, Bob cannot believe that that would be Alice, because someone else, in this case, an intruder, Trudy, can also impersonate that message and claim to be Alice. Right? So you need more information for Bob to trust that Alice is who she claims to be, right? So one of the things that you can do in a distributed system is to actually use the IP address of the machine where the packets are coming from as a way to authenticate, right? So you can say, if Alice in this case was a computer, right? So you can check, is Alice actually, are the packets coming from the IP address of the machine that's Alice's machine, right? So you could do this, but even this technique is vulnerable to what's called IP spoofing, where you can send IP packets with a fake address. So you cannot just believe because you got a packet over the internet from a certain IP address that it originated there, because you can spoof it. In fact, when we talked about web cluster scheduling, I showed you an example where the backend replicas were spoofing the address of the front-end switch, so that the user, the browser, believed that the HTTP response came from the same machine, right? So that's commonly used both for good and bad purposes. So if it's a bad purpose, then you cannot believe that the machine is actually Alice's machine, right? So you will get to a typical thing where you will use a password, right? So this is what we are familiar with. You have a username and a password, okay? So Alice can send a packet to Bob saying, I'm Alice, here is my password, okay? But if this text is going unencrypted over the network. That's a problem because Trudy can intercept this packet, extract the password, and then you can essentially log into the system claiming to be Alice. Right? So when you have communication back and forth, even if you have a username and a secret password, if this information is going unencrypted over a network, okay, that information is vulnerable to snooping by an adversary, and they can get your password. So there are protocols which no longer exist, but you should know, like FTP and Telnet, that essentially use this type of technique to log in. And they were unsecure, so we did away with that. We use things like SSH and SFTP, which are more secure, but we'll get to those. Okay. So that's version 3. That's not going to work. So what we will do instead is now use encryption for communication. So we will essentially use some way to provide secret information that's only known to Alice and Bob. Okay. So this is basically going to require that we use an encryption algorithm. I will just talk about it very briefly as to what encryption is, not go into the details, but you need to at least have a high-level idea. Okay? So an encryption algorithm is a function that takes an input, okay, and it takes a key, and it produces an output, which is the encrypted version of this. So if you have a string, let's say hello world, okay, that's your unencrypted text. You have a key, you feed it to this encryption function, it will produce another string, right? And the properties of the encryption function are, given the encrypted string, you should not be able to figure out what's the original message that was being sent. Okay? And you essentially need to use the key and that encrypted message, pass it through the same function to recover the original. So you can essentially use this function as a way to encrypt your communication. This is called an encryption algorithm. We will see some examples of this, but for now, just assume there's an encryption algorithm. We don't really need to get into the details. Okay? So all encryption algorithms need a key. Okay? The key is the thing that you're going to use to encrypt the algorithm. So the algorithm is going to be the same for all the users. The way it will differ from one user to the other is they have a key that's not known to anyone else. Okay? And that if you using that key, you can encrypt and decrypt messages. So in this case, we'll assume that there is a secret key which is known only to Alice and Bob. Okay? We'll call it some key K. So what Alice is going to do to authenticate herself is you'll basically take the username, okay, which is I am Alice, and encrypt it using that encryption algorithm and the secret key. Okay? So that basically gets you, this is now the encrypted version of the message. You are going to send it over the network. Bob is going to take the encrypted message. Okay? And so essentially the message that came, the secret key that's only known to the two of them, and decrypt it, and you get I am Alice back. And this allows you to now authenticate Alice because the key is only known to Alice and Bob. So you know that that message could not have been sent by anyone else. Okay? All right. So that's a version of the authentication algorithm that uses encryption. Okay? But this algorithm is actually vulnerable to what is called a playback attack. Okay? So what an intruder can do is essentially capture this encrypted version of the message. Okay? The intruder does not have the ability to decrypt this message because the intruder does not know the secret key. But that's okay because all that the intruder truly has to do is take that encrypted message and send it back to Bob saying, I'm Alice, and Bob will allow you to log in because Bob will decrypt the message and believe it came from Alice. Right? So encryption by itself didn't help us because this is now vulnerable to what's called a playback attack, where you don't know the contents of the message, you cannot extract the contents of the message, but you present the same message again to Bob, and now you essentially are able to prove that you're Alice. Okay? So we added encryption, that didn't work. We added a password, that didn't really work. So what should we do now? Okay, so here is where we'll get to this notion of what is called a nonce. So we will use our nonces, which are somewhat similar to one-time passwords, but in a different way here than what you might be familiar with when you use the one-time password. So what is a nonce? A nonce is essentially a once in a lifetime integer. So essentially from our purposes, it's an integer, okay? But it's something that you generate for every session. But once you generate it, you can never generate it again. So it's a once in a lifetime integer that you will generate for the purposes of authentication in this case, and you will never be generating it again for subsequent login or authentication attempt. Okay, so that's what we mean by nonce. So it's basically an integer that's one time and you'll never use it again. Okay, so here's our final authentication protocol. Alice will send a message to Bob saying, I'm Alice, username, right? So that's an encrypted message. Okay, Bob is going to generate a one-time non-integer in and send it back to Alice and say, prove that you are Alice with this integer. Okay? Now, Alice is going to encrypt that nonce. Previously, you encrypted your username. Now, you're encrypting the nonce with the secret key. And then you send that encrypted nonce back to Bob. Bob will decrypt it and verify that the nonce actually came back. So now you have authenticated Alice. Okay? Now, this technique is not vulnerable to playback attack because all that the intruder can do is capture this encrypted version of a nonce. But if you try to log in again, a new nonce is generated. So this one is useless because it's a one-time use only. Is that clear, what I just said here? Okay, so you can use this notion of nonces and just use the same type of encryption idea from the previous slide to get away from playback attacks, which are a problem if you use encryption. Okay, yes, question. Okay, so question is the first message, which is the username saying I'm Alice. We could just send a username, is unencrypted. What happens if that message is captured, right? So if some intruder captures that message, they'll know the username for Alice, okay? But they cannot do anything with this information to authenticate themselves. Yes, the username is known, but how will you log in? Because if you say present the username to Bob, Bob will send a new nonce. You got to encrypt it with the session asymmetric key that the intruder does not know. So you cannot just use the username to perform authentication in this case. Okay, you had a question, somebody? Yes.
When you are sending the nonce, they were supposed to have it.
Okay, question is there a timeout and when the nonce is actually going to expire? So in this case, there is no such thing as a timeout. This is a simple protocol. We don't worry about how long each message takes to go and come back. So you can take a while for the message to come back. That's okay. The main thing here is the nonce is never going to be used again once it's generated for any subsequent attempts by this or any other user. And then the second thing is the key that is being shared by Alice and Bob is only known to Alice and Bob, right? So those two, so long as those two properties hold, then this is fine, right? Of course, if somebody breaks into your computer and steals your key, all bets are off, right? Then the intruder can use the key to encrypt the message. So long as the key is secure and the nonce is never regenerated, this protocol is going to work. Okay. Any other questions here? All right. So that's nonce. So now we will try to make this slightly different, where we will use a different type of encryption algorithm, which is called public key cryptography. Okay. So this encryption algorithm uses two keys, not one. Okay. So typical encryption algorithm uses a single key. The same key is used for encryption and decryption. So the encryption key and the decryption key are one and the same. Okay. And they have to be known to both parties. Okay. And then so long as you have that key, you can either create an encrypted version of the message, or given an encrypted version of the message, you can use the key to decrypt the message. Okay. In public key cryptography, you have two keys, not one. Okay. So one key you can think of as an encryption key, which is also called the private key. The other is the decryption key, also called the public key. Okay. These two keys can be used to encrypt and decrypt. Really, you don't have to call them encryption and decryption. They're actually symmetric, but there are two keys in this system. Okay. And the way this is going to work is when a user creates a key, this pair of key, they'll take one key and they'll say, this is my private key. I will not share it with anyone. So that key is only known to that user. Okay. The public key you can give to any user. It's supposed to be public. Okay. So anyone can have that key. Okay. It doesn't matter even if the intruder has that key. So anyone can have a public key. Okay. But the private key is only known to that user. So that's the assumption. And now what you can do is, if you encrypt something with the public key, you can decrypt it with the private key. But the reverse is also true because it's symmetric. if you encrypt something with a public key, you can also decrypt it with the private key. Okay, so it is a symmetric protocol, but for now, assume that private keys are used for encryption, public keys are used for decryption, okay, just as an example. Okay. So how will we change our previous protocol to do authentication? We will assume now that Alice and Bob will have this pair of keys, but the private key is only known to Alice, because Alice is the one trying to do authentication. The public key can be known to anyone, but also known to Bob. Okay. So Alice is going to send the same message, I am Alice, username goes. Bob is going to say, here's a nonce, prove that you are Alice. Okay. So Alice will take the private key, encrypt the nonce, okay, and send it to Bob. Okay. Now Bob will use the Alice's public key, okay, and decrypt that message, and the nonce will be extracted. And then you will know that only Alice could have sent this key. Okay. Because no one else has Alice's private key, so only Alice can encrypt it. Okay. Now someone else, intruder, can also decrypt this message, because the message public key is known, but that's not going to do anything because you're just trying to do authentication in this case. Right? So from authentication purposes, the fact that you could decrypt Alice's message does not provide any value to an intruder. Okay? So you can still authenticate. Is this clear? Any questions here? So this is a more modern way of doing authentication, where you will essentially get a one-time nonce, and then you will use that to encrypt and send back. Okay, many authenticator apps that give you, I think the one that UMass uses gives you an integer once in a while, right? If you enter that integer, it's doing something like this, not exactly this, but something like that. Because there it's a 2-digit integer, so it's not a once in a lifetime. You only have 99 of them, right? Okay. All right. So that's authentication. But here are some more problems with this approach. So the problem here is how should Alice convey her public key in a secure manner to Bob? Because all of this assumes that Bob has somehow gotten hold of Alice's public key, right? So how did Bob get that information in the first place? And if you don't do that well, this is called distributing your key or key distribution. You can essentially break this protocol, even though it's secure from every other aspect. Key distribution can be a problem. So here's an issue that you could think about. So let's assume there's Alice communicating with Bob, and there's Trudy, the intruder, sitting in the middle. Okay? And we'll assume that Trudy can intercept messages that are going back and forth. Okay? Whether Trudy can decrypt messages is a different problem, but at least can intercept messages. Okay? So here's how things might work. Okay? So Trudy can impersonate Alice in the following way. Trudy can send a message to Bob saying, I'm Alice. Okay? So Bob is going to send a nonce saying, prove that you're Alice. Okay? Now, what Trudy is going to do is, Trudy is going to essentially send an encrypted version of the nonce, but Trudy does not have Alice's private key in this case. So Trudy can just use her private key and send it. Okay? So this is now an incorrect encryption because it does not actually use Alice's private key. Okay? Now, Bob, in order to decrypt it, has first got to get Alice's public key. Okay? So that has to be retrieved. So maybe you can think of a way that Bob is sending a message to Alice saying, send me your public key, okay? Which Trudy can intercept. Okay? And Trudy can respond pretending to be Alice, saying, here is my public key, and send her public key instead. Okay? Now, Bob does not know that this message actually came from Trudy. You can do IP spoofing and send that message, and believes that this is Alice's public key. So Bob is going to use an incorrect key to decrypt that message and get the nonce and believe that it's actually Alice. Okay? This is in the presence of a state-of-the-art encryption algorithm, which is public key cryptography. You can still break it. Okay? This is called a man-in-the-middle or person-in-the-middle attack, where the intruder is sitting in between, okay, and causing problems. Okay? Now, this does not mean that the encryption algorithm is the problem. The encryption algorithm is very secure. The problem is with key distribution. You do not have a secure way to distribute your key, and if an intruder can send fake keys to a computer or another user, then all bets are off. Right? So you want to make sure the keys that are being shared between two pairs are actually distributed in a secure manner. Right? So what this is saying is the encryption algorithm is only as good as the key distribution algorithm. You can have very secure encryption algorithm, but if you have a bad or a lousy way to distribute keys, it's not going to help, right? So another example, if you want to think, is maybe you think about you put a secure lock on your front door, okay, but you can put the key under the mat. Okay, it's not going to help. If somebody gets your key, they can open the lock. They don't have to break the lock. Right? It's the same problem. Our key is not distribution is not secure, so we want to make sure that part is secure as well. Right? Okay. So let's assume we know how to do key distribution. We'll get back to that in a few slides. But for now, assume it's secure. What can we do with some of these things? So let's talk about digital signatures as an application of all of what we just talked about. So in digital signatures, you are trying to sign a document, but rather than using an actual paper copy and using a pen, you are going to essentially sign it using a computer. Okay, so you are going to put a digital signature. How is that going to work? Okay. So the goals we want for any digital signature algorithm are that the sender cannot claim, okay, that they did not sign a message if they actually did. Okay, if you signed a message, okay, you shouldn't be able to claim you did not sign it, because there will be a way to verify that you signed it. Okay? And this, you cannot claim you didn't sign it. Okay? And the receiver should not be able to fake somebody's signature as well. And so you want these two properties. You want to make sure that if you sign it, okay, but you cannot later on claim you didn't sign it, and then someone else cannot use your signature. Right? So if you have these two properties, you'll get a digital signature algorithm. Okay? Here's how it's going to work. So let's say that Alice wants to sign a document, okay, or a message. It doesn't matter what the message is, doesn't matter what the document is. Just assume it's a string. Okay? It's a string of bytes. Okay? That's any arbitrary document can be represented as a string of bytes. So we will assume that Alice wants to sign the message. So what Alice is going to do is she'll take the document or the message M, okay, and she'll simply encrypt it with her private key. Okay? And this encrypted version of the document can also serve as a signed version of the document. Okay? Because the public key is known to everyone, okay? Because that's public. You can put it on your web page if you so wish. You can decrypt the document and extract the original content, but you can also verify that only Alice could have signed this document, because the private key is only known to Alice. So only Alice can generate the encrypted version of the document. No one else can. Okay? The fact that only you can generate it can also serve as your signature for this protocol. Okay? So one way to sign a document is to simply generate a public and a private key pair, use the private key to encrypt a message, and then say that the encrypted version of the message is the signed version of the document or the message. And then it can be verified. You cannot claim you did not sign it, because only you could have encrypted it. Okay? No one else can forge this, because your private key is only known to you, so only you can construct this version. So both of those properties will be addressed in this case. Is that clear? Okay. Okay. So this is a very simple way to have digital signatures, but it's not an efficient way. Okay? In fact, it's a very inefficient way, because public and private keys are very large in size. Okay? They're large because they have to be secure. So the larger the key, the more secure it is. Okay? But the larger the key, the more computationally intensive the algorithm is to generate the encrypted version. So this is a 100-page document you're signing. Okay? Your machine is going to take a while to generate the encrypted version, because it's taking a very secure algorithm and trying to encrypt that document. Okay? So it's not very efficient to encrypt and decrypt large documents with public and private keys as signatures. Okay? So you want to get this type of property, but in a more computationally efficient manner. Is that clear what I just said? Any questions there? Okay. So what can we do? Anyone have any thoughts? Yes. Okay, you could only append a small part, and only that part is signed. You kind of are on the right track. So you don't want to sign the full document, okay, because that's going to be computationally inefficient rather. So you want to sign something smaller, okay, and send it as the signature with the document. Right? So what is that you can use that smaller? You can use something called a message digest. Okay? What is a message digest? Message digest is simply a hash. Okay? Think of a hashing function. Okay? What does a hashing function do? It takes an arbitrary length string. You take that hashing function, you feed the string, it generates a fixed length hash. Okay? So you can get any arbitrary length string, okay? Input it into the hashing function, you get a fixed length, a smaller string. Okay? That's what property of a hashing function. Now the hashing function should have low probability of a collision, which means two strings should not produce the same hash. Otherwise, we are going to have problems. But good hashing functions already have that property. Okay? So here is what we will do. Okay? We will take a hashing function h to help us with making the digital signature more efficient. So we'll take the arbitrary length string m and we will generate a hash. Okay? So that's a fixed length string, much smaller than the original document, which could be arbitrary length. Okay? And then Alice is going to essentially encrypt the hash, not the original message, but the hash of the message. Okay? The hash of the message is the actual signature in this case. Okay? So you have the document M and you have the signature, which is the hash of your message. Okay? And you can take these two pairs and present it to someone. They can verify, okay, that you signed the message because they can regenerate the hash. Hashing function is supposed to be public. So you take M, which is the original message, generate the hash, okay, and then you can use the public key to decrypt this hash and verify that the two are the same. Then you know that Alice signed this message, and Alice cannot claim he didn't sign it, nor can anyone else generate this encrypted version of the hash. Okay? This is going to be far more efficient because hashing is a much cheaper operation than encryption, so just the hashing function. And then since you're going to encrypt a much smaller string, okay, the computational efficiency is bounded. Okay? It's not that is arbitrary length string. It can take arbitrary amounts of time. Yes. Yes. Question is, does this mean that anyone who has Alice's public key can verify that Alice has signed it? That is in fact true. Because the public key is known to anyone, you can verify that Alice signed it, because if you have Alice's public key, you can verify that you signed. Not very different from if you actually write your signature. So long as legible, somebody can say, yeah, that looks like your name there. So something like that. Right? So it's not supposed signature is not secret. You can verify it. Okay? So here are two properties of any good hashing function and also required for ensuring that this digital signature algorithm works, which is given a hash function h, you should not be able to find a message or construct a message that essentially gives you that hash function. Right? So if I just give you an arbitrary hash function, you shouldn't be able to generate some message that gives you that hash function, because if I give you some encrypted hash, and I could then take the hash and say, here's another document that gives me the same hash. Now you sign that document as well. That's the problem. So you shouldn't be able to take a hash value and construct a actual string that gives you that hash. Okay? So you shouldn't be able to reverse the hash function in another way. Right? And the second thing is collision probability should be low. You shouldn't have two strings that generate the same hash, because then you have the same problem. Because if you sign one document, then you can claim that you also signed that other document because it generated the same hash, because they collide. Right? So long as, and these are general properties of hash functions, they're nothing to do with message digests or digital signatures, but they're good properties to have for the hashing function to work well. Okay? Hashing functions are typically not invertible, and they also tend to have low collision probability. Okay? These are also called cryptographic hash functions. Not every hash function will have that property. Like mod is a hash function, mod n. That's not going to have this property. You'll have lots of collision. Every n integers will give you the same hash, for example. Right? But yes, in cryptographic hash functions will have this property, and then you can use them for digital signature. Okay? All right. So what kinds of cryptographic hash functions should we use? We'll not get into details of how to construct this hash function, but I'm going to mention some of them. Yes, for a very long time, there was a hash function called MD5, which is just an acronym, message digest 5, which was used to perform all kinds of hashing, was used in digital signatures and so on. But after a while, it became easy to break it, which means you could invert it. Okay? And then once you can invert hash function, is not secure anymore. So they decided not to use it. But 10, 15 years ago, when I taught this class, I said that's the one to use. for digital signatures, but now that's not the one to use. You should now use a more secure hash function. Once there's a family of them called SHA hash function. SHA just means secure hash algorithm. Okay, there's different families with different hash lengths. So that's the output length. Okay, so SHA-1 produces 160-bit, SHA-2 and more has basically 256-bit, 512-bit, 124 bits, and so on. Okay, so this was designed by NIST and NSA. Is still state of the art. Practically any encryption algorithm that needs hashing will use a SHA hash function. Okay, so that's the one that you should use if you are using things like digital signatures or any other thing that requires hashing. Is this clear? Any questions? Okay, we won't get into details, but you should. All of these modern hash function will have these two properties. Shouldn't be able to invert it. Collision probability should be low. Okay, all right. So with that, let me talk about one more thing, and then we'll get to secure email. So essentially, let's talk now about how are you going to do key exchange, because I said there has to be a secure way to exchange keys. Otherwise, we have all of these problems where if you send keys unencrypted, somebody can, intruder can get hold of it, and then you have trouble in terms of actually encryption. So how do you distribute keys in a secure manner? Okay, so that's a problem in itself. That's called key exchange, or key distribution. Okay, so you'll see two ways to do this. In one approach, we'll use a trusted third party. Okay, that trusted third party will actually generate the key and will give it to Alice and Bob in a secure manner. Then Alice and Bob can communicate with that secure key. Okay, so we'll use a trusted third party, which will be called the key distribution center. And then we'll see another algorithm which is decentralized. No third parties. You can essentially generate keys and exchange it in a secure manner. Okay, so two ways to do key exchange. Okay, so here is the one that uses the trusted third party. You have Alice on the left, Bob on the right. The key distribution center, which is called the KDC, sitting in the middle. Okay, protocol is very simple. Alice is going to send a message to the key distribution center saying, "I'm Alice. I want to communicate with Bob. Generate a key." Okay, the key distribution center is going to generate a secret key which is only valid for one session between Alice and Bob, which we'll call AB, which means it's a key for Alice and Bob. Okay, and that key is going to be sent to Alice in an encrypted manner. Okay, so the assumption behind key distribution center is that Alice has already a secret key that is shared with the key distribution center that can be used for secure communication. Bob has a secret key that's known only to the key distribution center and Bob that can be used for communication. So long as you have this, you can now bootstrap communication between any two pairs of users, because they don't need to have a predefined secret key. So long as you have a secret key that you share with the KDC can generate a secret key for any two pairs in the system to communicate with one another. That's the assumption, right? So you take this key KAB that was generated by the KDC, you encrypt it with the secret key that Alice and the KDC share and send it. Okay? You can do the same thing and send that to Bob. It's the same key. Now Alice and Bob have a key that they can use to communicate. So the case you are using the KDC to bootstrap your secure communication. Is that clear? Yes. Okay. Question is there a protocol to share a key between Alice and KDC and Bob and KDC? So in this case, that's going to be a recursive problem, right? So the way we will assume is that you have to bootstrap it in a secure manner, which is not an electronic means. For example, you actually physically go into the KDC office, they generate a key, they install it on your computer, you're done. You're not using a network to communicate. So you will assume there's an offline means to share that key. Once you have that, you're done, right? So that's the assumption here, because there is no secure way, because otherwise you'll have, we'll see another protocol which you can do away with KDC. You could use that, of course, to bootstrap as well. Is this clear? Okay. There's a variant of this where, which I didn't show here, where the key is sent by Alice to Bob, but this is kind of already showing the main idea, so I'll not go into that variant. Instead, what I'll show is a technique that does away with the trusted third party. Okay? So we are going to use public key cryptography for Alice and Bob to generate a session key. Okay? You could say, why do you need a session key if you already have public and private keys? Couldn't we just use the public and private keys to communicate? Why can't Alice just encrypt every message with the private key and then Bob can decrypt that message? Why do we need a separate key? Okay, so that's a question we should ask. And the answer is no different from what we had in the case of digital signatures. If you use public key cryptography, it's very expensive. The keys are very large in size. Okay, so that's going to make your encryption and decryption process really slow. Okay, so what you would rather do is use that secure key set of keys to generate a somewhat smaller key that's used for just one session, which will allow the encryption algorithm to be still very secure, but not very inefficient. Okay, so you want to essentially use public key cryptography to bootstrap a key. So here is how it's going to work. Okay, Alice is going to send a message to Bob saying, I'm Alice, here is a nonce. Okay, generate a session key. And Alice is going to take Bob's public key and encrypt that message. Okay, public keys can be used for encryption as well as decryption. Okay, so once you encrypt it, only Bob can decrypt this message because you need the other key to decrypt it. That key is only known to Bob. Okay, so no one else can get the hold of this nonce because it's now encrypted with Bob's public key. But Bob can decrypt this message and say, oh, this message came from Alice. Here's a nonce that came with it. Okay? Bob will generate any arbitrary session key. Doesn't matter. You just generate a long key. Okay, it's a big integer. So what you will do is you will send the nonce. You will send essentially the new nonce. Sorry, the old nonce. You'll generate a new nonce and the session key. This time, Bob will encrypt it with Alice's public key because that's also known. Okay? And that message can only be decrypted by Alice because no one else knows the private key. So Alice will get this message, extract the content, say that's the nonce that I sent. So that's the key that was meant for this session. Okay, and you'll get this nonce. You'll send that nonce back so that Bob knows that it's like an acknowledgement saying you got the message, the nonce has come back. Okay, now you bootstrap this session with a specific session key. You can then use that key to use a symmetric encryption algorithm, okay, which will be more efficient. Okay? So this is a way you can securely distribute keys. Is that clear? Any questions here? Yes. Yes, good question, and we'll talk about that as well. So this requires that the public keys were securely distributed in the first place, right? How did Bob and Alice get to know each other's public key? Right, so that's a question we got to ask, and we need an answer to that. Otherwise, you will say, send an unencrypted message to Bob saying, give me your public key. That can be intercepted, and someone else can send their public key, claiming to be Bob's public key, and you are back to the man in the middle attack. Okay, all right. So what shall we do here? So we will go back to a trusted server for secure distribution of public keys, not for distributing session keys, but for secure distribution of public keys. But this server is not going to be in the loop for every message exchange. Okay? Instead, it is going to be trusted for a different reason. Okay? What it is going to do is it's going to take any public key and it's going to sign that public key saying, I certify that that is actually Alice's public key. Okay? This is called a certificate. Okay? If you have actually gone to any SSL browser, you will see that there is a lock symbol that appears. You click on that lock, you get a certificate. So that certificate essentially is a public key that is signed by a trusted third party, so you can actually believe that it's somebody's public key. You don't just get a number and say that is Alice's key. Somebody is actually attested to that it's Alice's public key, and you believe that because you actually trust that whoever signed that key. Okay? So this trusted server is going to be called a certification authority. Okay? It has the authority to generate public keys that are signed, so that when they're presented, you can actually decrypt it and verify that that's actually signed. So I believe that that's the right public key. I don't get any public key and believe it's somebody else's public key. Right? So we will now use this trusted third party to essentially ensure that we will believe that somebody's public key. So now we don't need any secure algorithm. You can just freely send your public key unencrypted. Well, it's not unencrypted, it's signed, but you just send it, okay? And then so the other party can actually verify that it was signed by the certification authority. They'll believe you, right? So this is how modern systems will work. So here's what's going to happen. The first thing is you will again need to bootstrap this certification algorithm by storing the certification authority's public key on every system. Okay? Because you have to verify the signature. Okay? And the way this is done is like every browser is going to come with 100 different predefined certification authorities that are built into the browser. What that means is the public key of all of those trusted certification authorities are already pre-deployed on your system. Okay? So we basically don't have a protocol to share the certification authorities' public keys. They're actually stored in popular applications like browser, or any encryption algorithm will have certification authority key stored in them. In fact, if you go into your browser settings and go into securities, you'll see a list of certification authorities that are known to your browser. Your browser will only trust those certification authority signatures. If some strange signature shows, it will throw a certification warning saying, I don't know who signed this, I'm not going to trust it. Okay? So we'll assume that Alice and Bob have the certification authority's public key. Okay? Now Alice will go to the certification authority, say, generate a public key for me and sign it. So you'll get that public key, you'll get a signature that's called your certificate. It'll say, this is Alice, this is Alice's public key, here's a signature to verify it, which means you got a hash and you put a signature that you signed. Okay? So the way now, if somebody presents your certificate saying, I'm Alice, here's my public key, first you got to verify that it's correct. So you will take the trusted certification authority's key, okay, because and then you will verify the signature. The signature is signed with the private key that's only known to the certification authority. You have the public key. You'll generate the hash, the same digital signature algorithm. You'll verify that that's a valid private key, not somebody else's private key. Okay? So now you know how to get somebody's public key securely. Okay? So if you do that, then you can go back and make this part secure. And because this assumed that you had Alice and Bob's public keys, how will you do it? Alice will just present her certificate to Bob saying, here's my certificate, it has my public key in it, use this for any communication, and Bob will do the same. And we are done. Okay? This is what browsers do as well. When they actually connect to a server, the server sends its certificates to verify that that server is actually the website you're going to, not some bogus server that's trying to pretend to be some other website. Okay? Yes. How does the certification authority get public keys for new websites? So essentially, you have to go and request a certificate. Okay? And the certification authority is supposed to verify that you can't just show up and say, I am somebody else, give me a public key for that somebody else. They're supposed to verify that you are who you claim to be. So typically, if you're a user, you have to provide a passport or some form of identity before they would issue one for you. Okay? For an actual user, for computers, they use other techniques and so on. So if you want a certificate on a domain, let's say umass.edu needs a certificate so that the website can claim that they are. So you have to essentially show that you own the domain. And they'll only issue it to the domain owner. You can't just show up and say, give me a certificate for UMass, and then you can put up a website claiming to be the UMass web server. So they are supposed to verify this. And so that's a physical process. It's not an electronic process. Is that clear? Okay. So that gets us to certificates. So I'll talk about a few things, then we'll get to things like secure email. So security is much more than what I covered so far. It's a really complicated problem because all kinds of security issues that you have to deal with. We've only done very simple things like authentication and use of encryption to sign certificates and exchange keys. But there are a lot more problems you have to deal with. So typical enterprises have lots of systems in place to ensure security of different aspects of the distributed system. Okay? So you might have things like firewall that protect what traffic can go in and out. You have special types of firewalls that are called deep packet inspection or DPI firewalls that look inside encrypted packets to see if there are matching viruses in them and so on. Okay, there are virus and email scanners to make sure attachments that are coming on email don't have viruses in them. You can have network level security where you have Wi-Fi traffic is encrypted. You have passwords to get onto Wi-Fi traffic. You can have VPNs to communicate from external services, and all of the other things I talked about, certificates and SSL we'll talk about in just a second. Okay? So multiple aspects, and that thing, the list goes on and on. You will have websites that are secure. You can have one-time passwords to do authentication. Two-factor authentication now become very common. Okay? It uses some of the ideas we talked about, but not all of them. What we talked about are more secure versions than some of what's done here, but these are pretty good as well. Okay? And so on. Okay? So we will not have time to go into all of this, but I just wanted you to get a flavor of all the different things that have to be in place to secure a network and systems on. But I'll talk about one thing, which is what is a firewall, with one picture here. Okay, so this is a picture of a network firewall. Okay, what is a firewall supposed to do? Okay, a firewall sits between an internal network and an external network, and all of the network packets that are going out go through the firewall. All the incoming packets also have to go through the firewall. Okay, so here is on one side is our internal network. So this is a machine that's sitting here. On the other side is the external network. Every packet from any machine on this network has to go through the firewall to get out to the internet. Every packet that's coming from the internet to any machine inside the network has to go through the firewall. Okay? So essentially, we have now one box that's controlling all the traffic that's going in and out. Okay? So what can we do once we have this capability? We can essentially add what are called rules to this firewall that tell us what is allowed and what is disallowed. Okay? So the firewall can control what traffic is allowed and disallowed, on both directions. Okay? And this is done by specifying rules. Okay? Rules will be basically some way to tell the firewall saying, if the packet came from this type of machine and is going to this other type of machine, either allow it or disallow it. So they're called allow deny rules. So they're also called packet filtering. Okay? So every time a packet arrives to go out, it has to essentially, the firewall will check. It will look at the source address, it will look at a destination address, and it will say, is there a rule that matches this? Okay? And you will find some rule, because there's always a default rule, and that rule will tell you, is it allow or deny. If it says allow, the packet will be let out. If it say deny, then you'll drop it. So you'll essentially not allow that communication. Same thing for a traffic that's coming in. When a packet arrives, it has to match a rule for it to be let in. Otherwise, the firewall will simply drop it. Okay? So the default for incoming packets is, unless it was a session that started from the inside, just drop that packet. So the firewalls will not allow arbitrary traffic to come into your network. But the default is inside traffic can go out unless you added other rules to deny certain things. Okay? So this is a popular mechanism that's in place. If you have, let's say, a home Wi-Fi router that has a built-in firewall that is doing the same thing. Okay? It came with some default rules, so those default rules work. But you can add your own rules to do other things if you wanted to. Okay? So it's something you should know, because there's some things that you will actually find in your home networks and so on as well. But they're also used in enterprise networks to do more sophisticated things. Okay? You can do a lot more with firewalls than what I just talked about. You can actually look inside the packet. You can do forwarding, all kinds of other things. But this is by and large what a firewall will do for you, okay, and provide you with some degree of protection. Okay. All right. So I talked about all this, so I'll skip this and access control. Let's talk about secure email. Okay. So we have already talked about several different concepts. Okay. So let's try to put it together to make an application we are all familiar with secure. So you know email, right? By default, email is not secure. Okay. You're just writing some email, sending it out. Nothing is encrypted. That your email is going unencrypted. Okay. That's why you get spam, because you can't verify who sent it, what came, and so on. So can we actually make email more secure? So what does that even mean? What requirements do we want on our email? So here's one set of requirements. We can say we want secrecy. Secrecy means if I send an email to a friend, okay, only they should be able to read the content, okay? Not somebody who intercepts my message. Right now, if you intercept an email in transit, you will read its content, right? So you want to make it secret. Okay? You want to authenticate the sender and the receiver. You want to make sure if I receive an email, I can verify it came from whoever is in the from address. Okay? And vice versa, if I send an email to someone, I want to ensure that only the person named in the to address can read it, not any arbitrary person. Okay? So if essentially you want to do sender and receiver authentication, and you want something called message integrity, which means that no one altered that message in transit, that you didn't actually change the contents of the message and send it. Okay? So if you have those 4 properties, you can essentially get secure email. Okay? And whatever I just talked about in the past hour actually has all of the elements we need to build this. So I'll show you how we are going to build secure email. Okay? So secrecy. Okay? How will we do secrecy? Okay? We want to encrypt the contents of our email message. Okay? We already know something about encryption now. So what are we going to do? Okay? We could essentially take public keys and private keys to encrypt our messages. Right? So I can just say, I will take my private key, encrypt every message. I'll present my certificate, which has my public key, and you can verify. Right? So you can do things like this, but that's not very efficient. So we'll use something better. Okay? We'll use symmetric keys. Okay? So what we'll do is for every email Alice wants to send to Bob, Alice will generate a symmetric key K. Okay? Alice will encrypt the message with that symmetric key K. Okay? So now I have an encrypted version of my email. Okay? So now I'm going to take the key itself, okay, and I'm going to encrypt it with my my private key, okay, and I'm going to send this over. Sorry, not my private key, Bob's public key. Right? So you will take Bob's public key and you will encrypt the session key. Only Bob can extract that key. Okay? So you will send the encrypted version of the key and the encrypted version of the message. Okay? So now I took the message, I encrypted with the session key. I took the session key, I took Bob's public key and encrypted it. Okay? So only Bob can now extract the key because only Bob has the private key. And once you extract the key, you can decrypt the message. Okay? So we just use simple encryption, and we essentially got the first property, which is secrecy. Okay? Now this does not give us other properties, so we will basically not be able to just use this to get all of those properties, but we got the first one. Okay? But let's try to do other ones as well. Okay? So we know how to do secrecy. Can we do authentication? Can Bob figure out this message came from Alice? If I just get an encrypted message with a key in using my public key, I don't know it came from Alice. Anyone else can generate a message like this and claim that it came from Alice because nothing that Alice has that's in that message. How do we ensure that the message came from Alice? Okay? So this is going to require us to sign the message. This message was not signed. Right? The way you prove that you are sending something is use a digital signature. So let's do a digital signature version of email, but we'll leave secrecy aside for just a second. Okay? So Alice will use a hashing function on the message, okay, and get the hash, okay, which would be a SHA function. Okay? Then you will create a digital signature of that hash. Same thing we talked about. So you take a message, generate a hash, you sign the hash, okay? And then I send the message M, I send the hash to Bob. Bob can verify that Alice has signed the message. So at least I know it came from Alice. Okay? The message here is not encrypted. So we are not getting secrecy here, but we are able to know that you got the message from Alice. Okay? The previous one was encrypted, but we couldn't verify it came from Alice. This one we know came from Alice, but not encrypted. Okay? So this got us authentication and integrity. You can put both of these together and you will get all of our properties. Right? So this is our full secure email protocol. We'll take a message M, arbitrary length string that you want to send. Alice wants to send to Bob, construct a hash. Okay? Sign the hash. Okay? You signed it with your private key, so you can verify it. Okay? Then I take the message and the signed signature, and I make a new message M prime. Okay? So I took the message, I took the signature, I make a new message M prime. Now I do the secrecy part. I compute a key K, I basically encrypt M prime. Okay? Then I have to send that key securely, so I'll take Bob's public key, I'll encrypt the message, and then I take the encrypted version of M prime and the encrypted version of the key, send it over. So Bob can extract the key, decrypt the message, verify the signature, and you're done. Right? So although we had very simple building blocks, you can see that you can put them together to get some nifty techniques. I mean, none of this is actually done in standard email, but mail clients will support this if you actually go get signet certificates and so on. You can encrypt, sign, and what. Is this clear? Any questions here? Okay. All right. So I'm going to talk about SSL, and then we'll get hopefully to some digital currency concepts as well. So let me speak a little bit about how your browser sets up an HTTPS connection to the server. You already know how HTTP works. You use that in your clients and servers, but none of your traffic in your lab was actually encrypted. That's not how modern browsers work. All the traffic that's HTTP is actually encrypted between the browser and the server. So here is how it will work. So the browser will first send a message to the server, an HTTP message saying that I can support SSL, which is called the secure sockets layer. This is what is used to encrypt your HTTP communication. Okay? And the server will essentially send another message back saying, yes, it supports encryption. First, you have to make sure that both the client and the server support encryption. And the server, more importantly, will send its certificate saying, this is my public key. Okay? So the browser is supposed to extract from that public key the identity and verify that the server is actually legit. It's not some random server you connected to or spoofing an identity of a different server. So you are basically going to get the certification authority's private key and verify that certificate. Okay? The browser will do that. So once you've done this, okay, you used your list of CAs to verify this, then the browser will generate a key K. That's a session key. It will encrypt that with the server's public key that came in the certificate. Okay? And it'll send that to the server. Okay? As a future message will be encrypted. Here is the session key. Okay? And then the server can extract that key because it's sent with its an encrypted version of it is sent with its public key. So you can extract it and send the key back and say future messages will be encrypted. So now you just exchange the session key and you can use that to bootstrap communication. Okay? Not very different from what we talked about earlier, but this is explicitly using certificates now. First you exchange your certificate and then you use that to bootstrap a session key. Okay, so this is what will happen in your browser when you set up a HTTPS connection. HTTPS simply means HTTP running on SSL. Okay? You will still send regular HTTP messages, but the SSL layer will use that key to encrypt all the communication. At the other end, it will decrypt it. So at the application level, you still get unencrypted HTTP messages, but in transit, everything is going encrypted. Is that clear? Okay. All right. So one last thing, and then I think we'll wrap up. So we'll talk about electronic payments, and then we'll see how we can use some of these ideas to make some versions of secure currencies. Okay, so the first thing is how payment systems work. So this is nothing to a distributed system. These are just regular payment systems. So if you are using cash for your transactions, the way this works is you, as a payer, will then get some money from the bank. You'll go and buy something. You'll give cash. Okay? And then the merchant can then deposit that money into their bank. Okay? But when you use cash, you get an important property, which is anonymity. You don't actually reveal your identity. Okay? Cash transactions are anonymous. You go into a store, you pay something with cash, they don't know who you are, right? At least not from your cash. Okay? So that's a property we'll come back to. Okay? You can also use checks to make payments. So that's, you are familiar with that. Your bank issues your checkbook. You go as a payer, you write a check. The merchant will then present your check to the bank. The bank, your bank, and the merchant's bank will run what's called a settlement process. They will verify the check, they'll verify the signature, and then payment will go from your account to the merchant account. Okay? So there's now a settlement process involved between two banks for that transaction to take. Previously, the banks were not involved. Now the banks are involved. Okay? Same is true for credit card transactions. So you will essentially, the bank will give you a credit card, or some other credit card issuer will give you a credit card. You present that to the payee. The payee has to now run a separate protocol to validate the transaction. That's not shown here. You can go to MasterCard and Visa network to validate it. But assuming it's validated, payment goes to the payee. The payee will basically talk to your bank, and when you pay your bills, essentially money will get transferred to whoever this transaction went. Okay? So again, there is a settlement process that's involved. Right? Now, the important thing is, if when you use check and use credit cards, the anonymity part is gone because you're giving information about yourself, whether it's on your check, with your checking account, your information, or your credit card typically will have your name attached to it and so on. Okay? So you can now think about constructing electronic versions of this payment process by preserving some of these properties. Okay? So that gets us to our first protocol, which is electronic cash. It's not a real protocol, but I'm just going to illustrate to you how some of the anonymity of cash can be preserved in an electronic version. Okay, so here is how you can essentially construct an electronic cash. So let's say you are the payer. You want to generate a digital coin for $1. Okay? You'll essentially generate a coin, or you will ask a system to generate a coin for you. But to make it real, you're going to go to your bank, okay, and essentially ask the bank to sign it, so that when you present this coin to someone, they believe that is an actual $1 electronic coin, not something fake that you're presenting. So you want a bank to verify, or not verify, to sign this saying, yes, this is $1 that you can present, and if you present this coin to me, I'll give you $1. Right? So you want the bank to sign it, but if the bank is, let's say the coin has a sequence number on it, and you sign it, the bank has a record of it, that they issued your coin, $1 coin with this number, and when you spend it, they know that you spent it. So it can be traced back to you, whereas cash cannot be traced back to you. So if you want the anonymity property, what you're going to do is you're going to run a blinding process. Okay? What is a blinding process? Think about this coin. You'll put it into an envelope so that the sequence number is hidden, and you ask the bank to sign that envelope, not sign the coin itself, okay, so that whoever gets it says that this is actually signed by the bank, so I should trust what's inside it. Right? So you will basically blind the coin. You will essentially send the blinded coin, which will be signed by the bank. The bank will then send that signature, and then you can unblind it because of the bank signature and your $1 digital coin. Okay? So that you can then go and give it to a merchant. The merchant will have to validate that it's a valid $1 coin by going to the bank and verifying the validity. Okay? The signature is not enough to validate it, because you can do things like double spending and so on. Right? So you will verify the identity, and so long as it's a valid coin, you'll accept. Okay? So this is a form of an electronic cash protocol that was developed many years ago. It uses very simple things like signatures to get the job done, but never really took off. Right? Instead, we have cryptocurrencies and all these other things. But this requires a trusted entity, which in this case is a bank that's signing something that everybody believes. It has some properties of physical cash, so you can actually spend something without it being traced back to you. Okay, all right. So that didn't really go anywhere. What is actually used widely are cryptocurrencies, of which Bitcoin is one example. Okay? Bitcoin uses many different ideas that we have used in this class. It's a peer-to-peer protocol, decentralized, no trusted third party involved. You don't have a bank certifying anything. Okay? So it's an open source cryptographic protocol. Okay? Bitcoin has its own ways by which it generates currency to begin with. There are entities in the Bitcoin system called miners that are essentially going to be able to generate coins. Yeah, so, and there's a rate at which you can generate coin. Right? So miners are processes or computers in the system that serve multiple uses. A, they can generate currency, so you can have more currency in the system over time. But B, they'll play a useful role in the system to validate transactions. Because this is peer-to-peer, okay, you have to keep track of who is paying who. You have to say that this coin was transferred from this entity to this entity. Now it's owned by this other entity. Okay? But if you just present a Bitcoin to someone, how do they know you own it? Right? There has to be a way to track it back and say you are the owner, so you are allowed to spend it to begin with. But the Bitcoin is just a number at the end of the day. If you just present a Bitcoin identity, then you need to be validated. So you have to essentially be validated. The way it's validated is there is essentially a large ledger that's keeping track of all the transactions in the system. Okay? And the miners are the ones that are actually ensuring validity of all the transactions in the ledger. Okay? So essentially, as part of understanding Bitcoins, we have to understand what is a distributed transaction ledger, which also you not talked about. So we will essentially talk a little bit about this notion of a blockchain. A blockchain is essentially a distributed ledger. A distributed ledger is a distributed database. Okay? But in this database, there are two different properties that are different from a standard database. This is a database where all records are public. All the data in the database is completely public. Okay? There's nothing secret in there. Okay? And moreover, it essentially lists every transaction that has happened in the Bitcoin system, so you can track, okay, who is transferred, how much money to whom, who owns what coins, and so on. So it's all public, except that the identities of who is not necessarily public, because identities are simply public keys. Okay? They don't have to be tied to a particular person. You can just have public key that's a number, so you can't actually go back and see who that is. So long as you have that key, you can basically have access to all your currency, but you don't have to tell the system who you actually are. Okay? But there's a public key associated with all of these coins and so on. Okay? And blockchains are much broader used than cryptocurrencies. They are used for stock transactions. They are used for land transactions. When you buy and sell land, you can record them in a public ledger, marriage records, smart contracts. There are all kinds of use cases for blockchains where this type of property is important, where the information is public. Right? So all real estate information, at least in this country, all land records are public. So you know who owns a certain piece of land. So you can put that in a blockchain. It can be cryptographically signed. You can transfer it, and you can essentially do all of those things that blockchain allows you to. Okay? So we will now actually use this in the context of cryptocurrencies. So essentially, in this case, we want to sign every transaction with a key and insert it in the ledger. Okay? And then essentially, we will have a block of this transaction. We'll put it in the ledger. So that is done with Bitcoin's P2P protocol. Okay? So it has a peer-to-peer protocol where there are special nodes called miners. Every time you want to add a block, which is a set of records, to the ledger, you will ask the miner, can validate this block and add it to the ledger. Okay? So the miners have to now run a consensus protocol. Okay? Because you can't just arbitrarily add whatever you want. Then the ledger will have bad information, because if one of the miners is malicious, it can insert bad information. So you always have to run a distributed consensus protocol, okay, before you agree on, okay, we will all agree that this is the next record to add to our ledger. Okay? Furthermore, this consensus protocol has to have more secure properties than Paxos. Okay? Because Paxos does not deal with Byzantine faults. It can deal with crash faults, but here some miners can be malicious. So you want to ensure that even if some fraction of the miners are Byzantine faulty, they are trying to do arbitrarily bad things, the state of the ledger is always preserved. It cannot be corrupted by a fraction of the miner. And this goes back to our BFT properties, where you need 3F plus 1 miners to tolerate F faulty miners. Right? So if you have Byzantine faults, you will need a large number of miners to ensure that if some fraction of them go rogue or become faulty, the ledger integrity is still not violated. So we will use something which we have not looked at in this class, which is called Byzantine consensus. Okay? It is distributed. All consensus protocols are distributed, but this one does Byzantine consensus. It can handle Byzantine faults. Okay? We didn't look at that, but assume that such a protocol exists. So essentially, what is going to happen is, this is a big picture, but what essentially happens is you generate some entries you want to add to the ledger. You send it to the mining network. So this is a set of nodes that are sitting and running consensus. And the one that actually essentially wins that consensus essentially gets to add it, or the set of them get to add it to the ledger. Okay? And then for doing all of that work, okay, you will be rewarded. And the reward is, after performing a certain number of transactions, you will get a Bitcoin. Okay? And then you own that Bitcoin and you can spend it and so on. Okay? So miners are essentially rewarded for work. This is in the Bitcoin world called proof of work. So you have to essentially work to generate currency, and that currency gets added to the entire system. Okay? So that's the reason miners are even participating. Otherwise, why would you have machines that are doing all this work for not getting anything out of it. So the incentive is you participate in the Bitcoin network. Okay, after a while, you do a certain amount of work, you will get a Bitcoin. Okay? And the amount of Bitcoin that are generated is actually decreasing over time, so that the amount of money in the system is actually bounded. Okay? But that's a separate problem. We don't need to worry about that. But this ledger can then be essentially used for actually performing transactions. So if you have some Bitcoin in your wallet, you can go spend it, then you have to transfer it, and then essentially that transaction saying I spent X amount of Bitcoins on this transaction will have to go into the ledger and get recorded, which means that I am transferring my money to someone else, whoever I paid it to. Right? So that's how money is actually being exchanged. There's a public record of it, and you can always verify that when you're trying to spend it, you actually own it before you spend it. Okay? So that's the basic idea. It brings together some of the concepts we talked about, peer-to-peer networks, consensus, although this is using more sophisticated consensus than that we talked about. It uses signatures in terms of public key cryptography. So all these elements, you put it together, you get a cryptocurrency network. Okay? So that's all I'm going to say. There's a lot more here than I just glossed over lots of details, but you get a very high level idea of how security techniques can be used to bootstrap a cryptocurrency network. Okay? So that's all I'll say here. We'll wrap up the lecture. So I talked about a few different things. We talked a little bit about encryption and authentication. I talked about key exchange, and then we use these ideas to do several different applications, hashing, secure email. We ended up with cryptocurrencies. So this is actually important area of research, distributed security. Okay, the problem never goes away. No matter how many solutions you come back with, the bad guys come up with more issues that they can attack your network and so on. So there's never a dearth of problems to work on in this area. And also things like distributed consensus, etc., have gotten a big resurgence. Okay, Byzantine fault tolerance, nobody looked at for decades. And then once there was money in terms of Bitcoins, it became a big area, lots of papers now being published, people actually making companies out of it and so on. But also important from societal perspective that people need security to trust our computing system, right? So this is why when you design your applications, you really have to think about security as well. Okay, not something we did in the labs and so on, but still an important design concern. Okay, so if there are no more questions, I will end it here 1 minute early. So just to wrap up, we are done with the class. For those of you who came a little bit late, I mentioned that the exam is next Tuesday, okay, at 1 o'clock. Same thing as the midterm, you can bring one sheet of paper handwritten as a cheat sheet. And I also mentioned several times that you only have to worry about lectures 13 through 25. Okay? No need to worry about the material that was already on the midterm that we already covered. Okay? So best of luck for the exam and have a good summer. We'll stop here.